physics problems. Chapter 13, numbers 74, 76, 84, 86, and 87. Alright, number 74. So, The Little Prince, if you haven't read it, you really should. It's a good book. He lived on a tiny little planet, and scarcely bigger than a house. So, scarcely bigger than a house, well, it makes me think maybe it is a little bigger than a house. So, for my house-like planet, I'm going to assume that the house is 10 meters cubed. This dimension, this is actually really close to what my house is, about 10 meters by 10 meters. Mine's probably only about that high, but scarcely bigger than a house, so I guess there's the scarce bit there. So the volume of his little planet would be about 1,000 cubic meters. Now, the density is suggesting the density is the same as the Earth. So that means the mass, density is mass per unit volume. So mass of his planet over the volume of his planet, that's the density of his planet, would be equal to mass of the Earth over the volume of the Earth. So that means the mass of his planet is equal to the volume of his planet over the volume of the Earth times the mass of the Earth. And that's equal to 1,000 cubic meters over the volume of the Earth, which is a sphere, pretty much, 4/3 pi times the radius of the Earth, which is about 6.4 times 10 to the 6th meters cubed, times the mass of the Earth, which is about 6 times 10 to the 24 kilograms. So that should give us the mass of this little tiny planet. So let's see. When I multiply 1,000 times that, that's just going to bump that up by 3. So on the top I've got 6 times 10 to the 27th divided by 4/3 pi times the radius of the Earth cubed. Sorry, I just messed that up. There we go. So the mass of his planet is about 5.5 times 10 to the 6th kilograms. Pretty massive. 5.5 million kilograms. But that's just a tiny shade of that, right? So what are we trying to find here? We're trying to find the free fall acceleration of the planet's surface. So at the surface of the planet, I guess we need to find the radius of his planet too. We approximated it like a cube, but it's really a sphere, right? So let's see. The volume of his planet is 1,000 cubic meters. So 4/3 pi r cubed. So let's see. You need to take 1,000 divided by 4/3 pi, and then take the cube root of that number. So the radius of his planet's about 6.2 meters. And that jives with this, all right? If in the center of this to the outside, if this was a sphere, that's 6.2 meters. That seems about right. Okay, so now we want the free fall acceleration at the surface of his planet. Well, the acceleration, maybe by now we're okay with that's gm over r squared. It's just the other m divided out. So let's see what we've got then. G times the mass of his planet, which we found here, 5.5 times 10 to the 6th, divided by the radius of his planet squared. So that means the acceleration there would be about 9.5 times 10 to the negative 6 meters per second squared. Check and see if that jives with the answers here. Number 74. That's not what they have. Well, it's kind of close-ish. I guess they must have assumed bigger. They have about 2, so that's very close to. That could round to about 1 times 10 to the negative 5th meters per second squared, and they have 2 times 10 to the negative 5th. So, whatever. We'll let that go. I guess I just assumed a little bit smaller planet. And if I stick with my assumption here, then they also want for part B, what's the escape speed? So escape speed is 2gm over r. That's something you might want to pause for a minute here and think about where that comes from. That's an energy problem, how we derive that. That's something you need to know how to do. So let's see, that would be the square root of 2 2g times the mass of his planet, 5.5 times 10 to the 6th, divided by the radius of his planet, 6.2 meters. So I'm getting here that it's about 0.01 meters per second. In the book they have 0.02 meters per second. So again, I just assumed a little bit smaller planet, I guess, than they did. All right. 76. Very early simple satellite consisted of an inflated spherical aluminum balloon 30 meters in diameter. That means the radius is 15 meters. Always watch out for them diameters. And a mass of 20 kilograms. I suppose a meteor having a mass of 7 kilograms passes within 3 meters of the surface. So that's 3 meters from the surface. And that has a mass of, 7 kilograms. And they want us to calculate what is the magnitude of the gravitational force of the meteor from on the meteor from the satellite at the closest approach. So I think the trick in this problem, if there is a trick, is that the centers of these objects are 18 meters apart. So universal gravitational force, G m over r squared. Here would be G, mass of our sphere, mass of the whatever the thing is, 7 kilograms, and the distance between them is 18 meters. If you got this one wrong, I bet it's because you didn't have that 18 there. So let's do that. So G times 20 times 7 divided by 18 squared is about 2.9 times 10 to the negative 11th newtons. So not very much. And they put that in the awkward units of piconewtons. So but anyway, that's fine in scientific notation like that. And our answer agrees with theirs. Number 84. Uniform solid sphere of radius r produces a gravitational acceleration of ag on its surface. So we've got a sphere, radius r, and at the surface here, we're calling that acceleration ag. And they would like to know, at what distance from the sphere's center are there points inside and outside the sphere where the acceleration is ag over 3. So there's one on the inside and there's one on the outside. Well, on the inside, remember what the gravitational force looks like inside and outside. If you're inside something, then it's linear up to that point. You can review in your notes why that's true, and then it's inverse square outside. And this universal gravitational force, that's directly proportional to the gravitational field strength. So on the inside, if you want ag over 3, well, that's linear. You just have to go to here. That's going to be r over 3. Right? And then if you're on the outside, we want to find a place on the outside, then the universal gravitational force is equal to, and actually we don't want to know about force really, do we? We want to know what the acceleration is. We want to know that, so that's just gm over r squared. And we want to know where this is ag over 3, right? Right. But the ag itself so we're trying to solve for this r here. Maybe I'll make this a capital. Yeah, I'm going to make that a capital R so I don't get it confused with this R here. I know that this, at the surface of the planet, it's ag, so that's gm over that R that we know squared. Right? So plugging in things that we know into this equation, I can substitute here on this side of the equation. I have 1/3 gm over r squared is equal to gm over that r squared. So those cancel out. So that gives me 1 over 3r squared is equal to r squared. And this is the r I'm trying to solve for. So cross multiplying, r squared is equal to 3 times the radius of the planet squared. So the radius where we're going to get the acceleration that we desire here, that's going to be the square root of 3 times that radius. So that's about 1.7. That'd be about out here. So there's a spot here, 1/3 of the way from the center, and there's another spot here. That's the square root of 3 times out here. Cool. And what are we on? 86. Let's see. 86. An object lying on Earth's equator is accelerated toward the center of the Earth because Earth rotates, toward the Sun because the Earth revolves around the Sun, and also toward the center of the galaxy because that's rotating. So there's a centripetal acceleration associated with each one of those. and I'd like us to find what that is, and as multiples of the Earth's, as multiples of g, which is 9.8 meters per second squared. So the first circle that we're moving in, if we're on the equator, is this circle here. So the centripetal acceleration required for that is the centripetal acceleration, no m in that. I was thinking centripetal force, that's mv squared over r, but centripetal acceleration is just v squared over r. So let's see if we can figure that out. And of course, v is equal to 2 pi r over t. So we just need to figure out what that is for each of these. Maybe we'll do that up here. So the velocity of the circle, let's say this is v1. So that's the first circle we're moving in. So for v1, it's 2 pi. The radius of this circle is just the radius of the Earth, which is about 6.4 times 10 to the 6th meters, over the period is 365 days. So that's 365 times 86,400 seconds. So let's figure out that speed. How fast are we going in that circle there? So that's 2 pi r divided by 365 times 86,400 seconds. So that's about 1.27 meters per second. Oops, you know what? That's totally wrong, isn't it? Because the Earth revolves on its axis once a day. So that shouldn't have been there at all, right? That's just one day. It's not a year. That's what we're going to use in the next one. So I shouldn't have divided by 365. So if I multiply that by 360, there we go. That's right. Sorry about that. So about 465 meters per second. All right, let's find the rest of these velocities. So the second circle we're moving in, that's the one that takes a year as we're going around the sun. So that circle is 2 pi times the radius of our circle around the sun is 1 astronomical unit, which is about 1.5 times 10 to the 11th meters. And that takes a year. That's 365 times 86,400. So let's try that. 2 pi times 1.5 times 10 to the 11th divided by 365 times 86,400. So that, going a little faster there, that's 30,000, close enough. So 30,000 meters per second. And then the big circle we're moving in is 2 pi times our distance from the center of the galaxy, which is 2.2 times 10 to the 20th. Divided by how long that takes. And that takes 250 million years. So let's see, that's 250 million years times 365 days in a year times 86,400 seconds in a year. Let's see how fast we're moving in that circle. So 2 pi times radius of this big old circle, many light years across, and then we got 2.5 times 10 to the 8th times 365 times 86,400. And that's about 175,000 meters per second. Hold on. So this is like some crazy carnival ride we're on. Going in this circle, and while we're going in this circle, we're going in this bigger circle even faster. And while we're going in that circle, we're going in this circle even faster. So that's crazy. Definitely would make me sick, that kind of ride. So let's see. Let's find the centripetal acceleration for each one of these, and then we're going to do it as a multiple of g. So centripetal acceleration for our first circle, our local circle, is v squared over r. The radius of that circle is the radius of the Earth, which we used 6.4 times 10 to the 6th. So 465 squared over 6.4 times 10 to the 6th. So that's 0.034 meters per second squared. And if we want to do that as a multiple of g, then I'm just going to divide it by that. So that's 0.0034 g, or 3.4 times 10 to the negative 3 g. There's our first one. Now for the second circle, we're going at about 30,000 meters per second squared over the radius of that circle. It's an astronomical unit. So that's v squared, 3 times 10 to the 4th squared over 1.5 times 10 to the 11th. That's 0.006 meters per second squared. And as a multiple of g, that's going to be about 6.1 times 10 to the negative 4th g. And then finally, in our biggest circle, we are going 175,000 meters per second squared over the big circle, about 2.2 times 10 to the 20th. So 175,000 squared over the radius, 2.2 times 10 to the 20th. Ooh, dear. That's 1.4 times 10 to the negative 10th meters per second squared. As a multiple of g divided by 9.8, that's about 1.4 times 10 to the negative 11th of our Earth accelerations. So that's worth kind of thinking about a little bit, what's going on there. We're moving faster and faster in those circles, but the centripetal acceleration is decreasing pretty quickly here because the radii of those circles, they're getting so much bigger, and that's dominating what's happening here. So if you think about like what we feel because we're moving in these circles, even this, that's just such a tiny fraction of our gravitational acceleration. That's how much acceleration is required to keep us moving in the circle that we're going in because we're on the Earth. So compared to the massive 9.8 meters per second squared that we're feeling because of the gravitational attraction, this is tiny, tinier, and like super ridiculously tiny. That's technical physics talk there. Super ridiculously tiny. Last one, 87. If the legendary apple of Newton could be released from a height, this is similar to one that you did recently, from a height of 2 meters above the surface of a neutron star with a mass 1.5 times the mass of the Sun, and with a radius of 20, did I see that right? 20 kilometers. Then what would be the apple's speed when it reached the surface of the star? And we're releasing it from 2 meters. So we can figure out the acceleration first at this neutron star at the surface. That's gm over r squared. So let's see. That's g times the mass of this thing. It's 1.5 times the mass of our Sun. The mass of our Sun is about 2 times 10 to the 30th, so that would be 3 times 10 to the 30th divided by r squared. That's 2 times 10 to the 4th squared. So we have a gravitational acceleration a whopping 5 times 10 to the 11th meters per second squared. So that means in part A, a little kinematics problem, initial velocity 0. I'd like to know how fast it's going to be going. I think that's what we're looking for, isn't it? What will be the apple speed? Yes. So the delta y is going to be equal to 2 meters. I'm taking down to be the positive direction because that's the only direction we're going in here. Right? So we did this before. So Vf squared is equal to the Vi squared term is 0 plus 2a delta y. So Vf is equal to the square root of 2 times 5 times 10 to the 11th times delta y, which is 2. So root of 2 times 2 is 4 most of the time, times 5 times 10 to the 11th. So it'd be going about 1.4 times 10 to the 6th meters per second. Pretty fast. Then they also want us to calculate if the apple could rest on the surface of the star, what would be the approximate difference between the gravitational acceleration at the top and the bottom of the apple? So gravitational acceleration at the top and the bottom. I don't know if you've been to the grocery store recently, but the whole apple thing has changed very much, certainly since when I was a kid. We used to get, apples were all sort of lunchbox sized apples, and now there are these big apples that, apples cost like, let's say, $3 a pound. Buy one apple and it's almost a pound. It's like a $3 apple. $3 for an apple. That's crazy. But they're good, these fancy new apples that they have. So I'm going to just say that, 10 centimeters? They're definitely apples that are that big these days. So I'm going to go for that because it's an easy number. So let's see. The difference in the height of the apple from the top to the bottom is about 0.10 meters from here to here. So what difference does that make? Well, the gravitational acceleration the surface of the planet is gm over r squared. We found that. That's 5 times 10 to the 11th meters per second squared. And that would just be at the bottom of the apple, right? What about at the top of the apple? Well, that would be gm over r plus 0.1 squared. It does not seem like much, does it? But these are big numbers, so let's see what happens if we do that. So let's see. The top of the, well, just think for a second. It's going to be both intuitively, would there be more or less acceleration at the top of the apple? Think about that. It would be less, right? Because it's further away from the center of the planet. You can also see we're dividing by a bigger, only slightly bigger, but a bigger number here. So let's see how much of a difference. So let's see, g times the mass was 3 times 10 to the 30th, right? 1.5 times our sun, divided by the radius of this thing was, what was it? I forgot. There it is. So it's 20,000, so it's 20,000.1 squared. So that's, I think I needed to keep more decimal places, didn't I? I'll have to go back to this number again. So this is 5.0024 meters per second squared. And then this number, go back, and this is 5.0025 meters per second squared. So something like that. And this is actually 245, and this is 25 exactly. So, I mean, those numbers are different. They look very, very similar when they're in scientific notation. That's times 10 to the 11th. Sorry, times 10 to the 11th. So what is the difference between those? You take this number here and you subtract 5.00245 times 10 to the 11th. Well, that's a difference of 5 million meters per second squared. So that's pretty massive difference. If you want to turn that into force, you could think about multiplying like the mass of like the top part of the apple times the mass of the bottom part of the apple. But there's like a massive difference in force. Let's say on the order of, I think, 100,000 pounds of force, something like that. So you know what happens if you put 100,000 pounds on top of an apple? Yeah. So that answers that question. The moon, as you probably already know, is made of cheese, and neutron stars are made of applesauce.